In this video, we are going to start to talk about gases and how they move and how they behave. So the first thing we have to do before we get to that is we're going to address this thing that you've probably seen before called STP. So STP stands for Standard Temperature and Pressure, and basically all it is a temperature and pressure that scientists at some point decided was going to be the standard. All right, and so you see this a lot. It can be put into almost any question, whether you use it or not. It's found on your reference tables on the front page. It's actually the very first table, Table A, Standard Temperature and Pressure. You may want to highlight the S, the T, and the P, or, you could always put, STP off to the side on it, just so that you know. Because sometimes they'll abbreviate it, and other times they'll actually write it out, so it depends on what they do. So standard pressure is either 1 or 1.3 kPa, which stands for kilopascals. Pascal is the unit, kilo just means 1,000 of them, and 1 atm, which is atmospheres. Now these pressures are the same pressure. Okay, so 1 atm is 1 or 1.3 kPa, so you could swap these for each other at any time. And then standard temperature is 273 K or 0 C. They are the same temperature. Now, for gases, we are going to use Kelvin only, and the reason is when you eventually learn our ideal gas formula, you don't want to have a zero in the denominator, so that's why we use the ideal gas formula. But that's pretty much it. So standard temperature, standard pressure. Now let's get to what we call KMT, or the kinetic molecular theory of gases. If you read it backwards, it explains exactly what it is. We know molecular means movement, molecules. Kinetic means movement. Molecular refers to molecules, and theory is just an idea. So it is the theory or the idea of how molecules, specifically gas molecules, move. So if you read it backwards, it explains what it is. So this is how gas molecules move. Now, they can be broken up into two categories: real versus ideal. Real gases are what happen in the real world. We are going to mainly focus on ideal. The easiest way to do it is to memorize the ideal, and then just know that real gases do the exact opposite of ideal gases. Now, the reason we use ideal versus real is simple. In an ideal setting, the math works out very easy. In a real setting, the math is very complicated. And so that's why we're always going to work on ideal gases, but we do have to be aware that real gases exist. So ideal gases, how do they move? They move rapid, random, and straight. So they're moving very quick. They're moving randomly. You can't predict which way they're going to go, but they're always moving in straight lines until they collide, and then they move in a different direction, but also in a straight line. When they collide, they transfer energy without loss. So basically, if you think of that desk toy that everyone's seen, I think it's called a Newton's Cradle. It's the one where you have there's like a little hanger, and it's got some like steel ball bearings on it, and then you kind of lift one up and it bangs into the other, and they just go back and forth, right? Well, in real life, that thing slows down because every time they collide, right, if you envision those as gas particles, every time they collide, they lose a little bit of their energy due to friction. Some of it's due to the sound that they make, so they do lose energy every time. If they were ideal gases, then they would actually never stop, and there would never be any slowing down due to friction or anything like that. So we say that they transfer energy with no loss of energy when they transfer. They have no volume. What that means is pretty simple. If you look at a gas molecule or a container that has gas molecules in them, the molecules themselves are so small compared to the space that they take up that we can ignore the volume of the atoms themselves. So an example would be if I were to draw out the phase diagram for a gas, you'd have a little box, and then you'd have a bunch of dots, right? And that'd be my gas. Basically, what we're saying is, if we took the volume of the atoms themselves and compared it to the volume of the entire space that they occupy, it would be so small that we can just ignore it. So we say the atoms themselves take up no volume. That's obviously not true, but again, we're trying to make the math easy. And the last one, there is no attraction between gas molecules. So now, when we think of atoms, they have, you should know this at this point, but if you didn't, it's fine. They have positive and negatives, protons and electrons inside of them. They have other things inside of them too, but we'll explain that later on in the year. Point is, they are like little tiny magnets. And when little tiny magnets get close to each other, they do have a tendency to attract in the real world, hence the real gases. But that makes it very difficult to predict what they're going to do, and their math gets all wonky as well. And so therefore, we say that there is no attraction between gas molecules, but we know that's not true. Now, that attraction actually has a name. It's going to come back throughout the year over and over again, so you may want to get used to it now. It is called an intermolecular force of attraction. What that means is it is a force of attraction that's intermolecular. Molecular refers to molecules, and inter means it's between two different molecules. So basically, it's a fancy way of saying two different atoms or molecules are attracting to each other. All right, that's all intermolecular force of attraction means. Real gases just do the exact opposite. So think about the word. What's the opposite of rapid? Well, you could call it slow. I'm going to use the word slow. Random would be predictable, and straight would be curved. All right, so that's my opposites. Now, if you used a different one, that, you know, if you used a different synonym or antonym, then that's fine. It doesn't really make a difference. When they still collide, but the difference is instead of no energy loss when they collide, there is energy loss. So this would be the Newton's cradle in the real world. It will slow down and eventually stop. Just like if I bounced a ball on the ground, eventually and I just left it, right? Eventually you would see that bounce would get smaller and smaller each time, and eventually it would slow down and stop. And so that's transferring energy. That is the energy loss that we're referring to. Real gases have volume as opposed to there is no volume. Real gases have attraction as opposed to no attraction. So the way I like to do it, since we use ideal the most, memorize the ideal, and then just know that the real, you just have to negate them or do the opposite. All right, and last part. We can make real gases behave ideally if we separate the molecules. It's like having a bunch of little kids. If I have a bunch of little kids and I put them all in a room and I don't supervise them, they're just going to go crazy. They're going to start interacting with each other. That would be the intermolecular force of attraction coming into a play. So they're going to interact with each other. They're not just going to sit there and pretend like everybody else isn't there. So if you want kids to behave better, though, one way of doing it is to, instead of having, 20 kids in a tiny little room, maybe put each kid in their own room, and then their behavior will get better because they'll have nobody to play with. So the way you do that, the way you separate molecules, is by having a high temperature that makes the molecules expand and start moving faster, and a low pressure that also allows them to expand and get further apart. So high T, low P is another way of saying it. That will make an ideal gas or a real gas behave ideally. Last part, we'll talk about the two relationships, and then we are done. So the two relationships we have to worry about are called Boyles Law and Charles Law. Boyles Law is the relationship between pressure and volume. Charles is temperature and volume. So here's how it works. If you increase the pressure on a gas, don't worry about the doubled and the halved, because that is true for an ideal gas, but we'll just go even simpler. So here I have a cylinder, and in that cylinder there's gas, obviously, and I have a little there's a little handle or and a thing that closes it off at the top. Basically, if I apply pressure by pushing down on this top right here, the gas is going to shrink. That's how gases work. You've definitely seen that in everyday life. We'll do a lab where we do exactly this, so it'll make it a little bit easier. And if I were to let go of this top and stop applying the pressure, then the gas molecules will push it back up. That's the idea. If you squeeze a gas together, it's going to get smaller. The key is you have to squeeze it from every angle, meaning if you try to do this with a balloon, if there's any gaps like between your hands, then the balloon is just going to try to go out the gap, and so it won't work. So you really need to have a sealed system in order to actually see this effect. A balloon wouldn't be the best. So pressure up, volume down. It's pretty simple. The graph, if you were to graph it, and we will graph it eventually, looks like this. Last part, Charles Law. This is the temperature relationship, temperature-volume relationship, and this is real simple. If you heat a gas up, its volume is going to expand. And if you cool a gas down, its volume is going to shrink. So it's pretty much direct versus indirect. Pressure volume is indirect or inverse, whereas temperature volume is direct. And there's no other word for that. So it's direct. So that is the explanation of the two relationships. The last thing, or the next thing we're going to do, is we're going to learn the ideal gas formula, which puts both of these relationships together. So then we can see how temperature, volume, and pressure all affect one another when we have a gas in a given system, and then we change stuff to it. So that explains everything on this video. If you have questions, just message me.